So I made a previous video on row space, and we saw that matrices have the same row space if and only if their row canonical forms have the same non-zero rows. Now for the column space, there is a small trick here. So we are going to determine whether the following two matrices, A and B, if they have the same column space. Okay, so A and B will have the same column space if and only if the transposes A transpose and B transpose have the same row space. Okay, so we have to take the transpose of A, and then we take the row canonical forms, okay, and if they have the same non-zero rows, then they will have the same row space. Okay, so first I take the A transpose, so that will be 1, 1, 1, columns will be rows, okay, and then I reduce it. Of course here I jumped a couple of steps, okay, and I got this matrix. So we take the transpose of B, B transpose, so 1, 2, 3, minus 2, minus 3, minus 4, 7, 12, 17, and then what we do is, so B transpose, row reduced to its canonical form, 1, 0, 3, 0, 1, minus 2, 0, 0, 0, and we see that A transpose and B transpose, they have the same row space. So since they have the same row space, A and B will have the same column space. Okay, let us see how useful this concept of row space and column space is. So we have vectors u1, u2, and u3. So u1 is 1, 2, minus 1, 3. u2 is 2, 4, 1, minus 2. u3 is 3, 6, 3, minus 7. And we have vectors v1 and v2. v1 is 1, 2, minus 4, 11. And v2 is 2, 4, minus 5, 14. And let us call u the span of vectors u1, u2, and u3, okay? And let us call w the span of v1 and v2. And now we want to show that the space, they are all subspaces of R4. This is obvious, right? Well, it's obvious that they are all in R4, but they are all subspaces of R4. Okay. Let us show that U, so the space spanned by these vectors, is the same as W, the space spanned by these vectors. Okay. Okay. We have two ways. I'm not going to do the first one. The first way is to pick every single vector u1 or every single vector v1, like we pick v1 and we do u1, u2, u3, alpha, beta, and gamma here. Okay, so we show that every single u is a linear combination of vectors v, and we show that every single v is a linear combination of vectors u. Okay, so if we do this, we will prove that u is the same as w. But this is going to be a bit of a tedious work, right? Because we are going to take 6 systems to do all this. Okay? Okay. We have a second method for this. So this second method I think is really handy. So we built a matrix A with the vectors u1, u2 and u3. So 1, 2, minus 1, 3. So we put all these vectors here. And we built a matrix B with vectors v1 and v2. 1, 2, minus 4, 11, 2, 4, minus 5, 14. And now we have to row reduce it. So if I did not make any mistake, the row reduction with row reduction I get for A 1, 2, 0, 1 third, 0, 0, 1 minus 8 over 3, and for B I get the same row reduction, right? So since the non-zero rows of the reduced matrices are identical, the row spaces of A and B are equal. So since they are equal, U is equal to W. So they generate the same space.